Welcome, thank you. And the title of my portfolio, it's evolved a little bit from last year. I had two areas I covered last year. Was the sensing, and then it was a gigahertz, terahertz materials and electronics, which will be presented tomorrow by Dr. Jim Huang in the morning, I believe. And so now I'm focusing on sensors and detectors. And so the title here is Adaptive Combinatorial Multimodal Sensing Physics and Methods. It's really looking at optimum combinations of multimodal sensing capabilities to give the warfighter greater capability to do his exploitation. Next slide. Uh-oh. Okay. Stop the clock. Yeah, okay, go ahead. Those are 4 pixels. Okay, back. Okay, so the vision. It's basically looking at novel materials, material science, novel material structures, new device constructs, physics, and implementation schemes that can lead to breakthrough generations of adaptive, intelligent, compact sensing for future adaptive and autonomous ISR. And I'll have a couple slides that will provide motivation for why we need. Next slide, please. Okay, that's the mandatory slide. So my portfolio has 4 different thrust areas. The first is heterogeneous nanostructure design and synthesis. This is, in general, heterogeneous material systems it's the holy grail of semiconductors, right? If you look at the periodic table, there are very few elements that are compatible, have the same lattice constant. And it's an area that requires a lot of work. For example, if we had breakthroughs, we'd be able to have 50% solar cells, and you'd be able to put optical capability on the silicon wafers and whatnot. And I'm focusing on actual embedding nanostructures into bulk semiconductor with the aim of reducing and mitigating strain and also the electrical defects that occur at the barrier. The second one, thrust, has to do with new phenomenology of interactions between photons of signatures coming in and these new nanostructures with an aim at coming up with new transduction capabilities. And the last one is looking at new mixed mode being spatial, spectral, polarimetric, maybe phase capability within the same material system and construct. And there's 3 sub-thrusts. The first is looking at new ways of constructing filters on top of say, a photodetector that allows you to adaptively tune the wavelength and the polarimetric information that reaches the lower layers. The second little thrust area is looking at combinations of new materials that can adaptively be able to control which wavelengths and polarization properties can be absorbed further down. And then the last is conductive conduits and transparent interconnects to get the signal out of future devices. And then the 4th one is kind of a catch-all. I just have really a few programs in it, looking at these micro coolers that could potentially be integrated into focal plane arrays, and some memory exploitation projects in it, and then solar PV, which are essentially a number of STTRs. Next slide. Okay, motivation. So that list was really material science and device physics, very pervasive for many applications. Each year that I provide motivation, I change it. I think the first couple years it was space situational awareness, and then it was layered sensing. And so now I'm moving on to some of these challenges that are very crucial facing the Department of Defense in terms of the enormous amount of data that's being generated. There's this information on war, should be information in war, explosion. Of course, we have these new global threats. The long-standing Cold War large armies, those no longer have. We have deeply embedded insurgents that are elusive. They're in many locations. And so there is a need to have this persistent, 24-hour-a-day, eyes in the sky over large, vast amounts of areas. And consequently, the military has turned to these autonomous ISR platforms that consequently are greatly, they're producing so much data that the communication links and exploitation methods are not keeping up. And this is just a quote from the Honorable Zach Lemnios. He reported this to Congress, saying that the warfighters are swimming in sensors, drowning in data. The analysts are overwhelmed, and data to decisions and autonomy are actually two of his seven magnificent strategic priorities. Next slide. So we have this is just showing you the kill chain here. So we have the sensor data explosion. So again, more global hotspots, more eyes in the sky, more data, bottlenecks in bandwidth and exploitation. Part of the problem is that, again, the sensors are generating way too much data. The numbers of sensors that are being deployed are constantly increasing. And these arrows here represent the communication links. In large part, they're not, their capabilities are not expanding. These are like 275 megabits per second. And then when the data finally gets to the guys, the analysts on the ground, this is they're calling PED, processing, exploitation, dissemination. They're not able to handle it. In fact, they're able to process about 5% of the total amount of data coming in. The rest of it's redundant. It's not useful. It's actually thrown away. Next. Okay. And so I just wanted to show where all this data from these UAVs is coming from. Of course, over in Iraq and Afghanistan, we've been using the Predator, the Reaper, the Global Hawk. The Predator's being phased out for the Reaper here. And we're currently, the sensor ball in the front has two focal plane arrays. It's generating at least 500 megabits per second. So it requires actually two full data links to be able to handle this amount of data. Now, just last year, they've updated this. They've added 2 additional pods. It's called Gorgon Stair, and it has 9 focal plane arrays, 12 viewing angles, and it is generating so much data that they're unable to transmit it back to the pilots that are flying the UAV. They're having to send it down to Humvees on the ground. There's crews that take that information and do the processing exploitation and give the data to commanders. And in a very short while, they're upgrading that Gorgon Stair up to having something like 50 spots on the ground, which is just an enormous amount of data. And then after this, we're talking about something called Argus, which has on the order of 2 billion pixels, 2 billion pixels. They said it would require all the communication links that the military has total to handle all of that information. And so they recognize the need to be able to make decisions on the platform itself of what data is important, what's most relevant in terms of decision making to send back to decision makers. And this also shows the plans here. I know this is very difficult to read, but today they have on the order of 50 motion imagery spots, okay? And they're planning to go, General Deptula, before he retired, he put together this 50-year plan for the UAVs, planning to go up to something 4,000 motion imagery spots, from 50 to 4,000. So that's just an enormous leap and increase in capability and in terms of generating enormous amounts of data. And obviously there's going to have to be advancements made not only in sensing, communications, high-speed processing on orbit, and also new tools, information exploitation tools that the analysts will have on the ground. And one more thing is, in addition to these very complex focal plane arrays on these platforms, there are war planners looking at implementing nano, micro, and smaller vehicles that will even be generating even more discrete sets of data. And so the message here is we're moving into a paradigm where enormous amounts of information will be generated, and there's going to have to be some increased level of sophistication of sorting through that data. And we go to the next build. And I think that part of the solution possibly could be coming up with new sophisticated, not necessarily too sophisticated, but entirely new classes of detectors that are smarter, more capable, compact. The smarter and more capable have to do with real-time adaptive sensing. And this could be controlled by the cognition, a man on the ground that has a little joystick deciding what colors he wants, what pixels he wants, or later it will be more autonomy, it will be machine autonomy, artificial intelligence and whatnot. But in the near term, it should be, please next slide. In the near term, I believe it's going to be these operators, and by the way, this is a brand new position in the Air Force. They're hiring young smart guys out of high school and college, that's all they're going to be doing, is just looking at data at a console, making decisions of how to do their exploitation and dissemination. And I can kind of envision that there'll be some guys in the future that are sitting at either common control consoles, or they could be back in the United States, and they have these knobs to turn in real time. It's like in a video game, right? And they're looking at a target, and they have 10 million pixels, and they say, wow, I see this one little area over here that looks really interesting. We saw some movement there, and they'll zoom in on it, and then once they've zoomed in on it, they have reduced the amount of the bandwidth required, right, by, it could be a factor of 10,000. And in addition to that, then they have the ability to say, wow, I want to see this in several colors, and I want to get some polarimetric information, because that's going to allow me to see edges. It's going to be, and the different colors will allow me to increase the reduction of the clutter, and it's going to help me understand what the material is. And so I truly think that this is, and there's a precedent for this. There's been a lot of calculations done for pattern recognition algorithms, and these algorithms have proven to be able to exponentially reach a knowledge objective by having more layers of independent information. Okay, and that's what I'm talking about here. Basically, is just being able to, within a pixel or some other construct that I'm going to talk about in a few minutes, be able to, looking at that signature come in, pick off the pieces of the information from the photon stream, hundreds of photons maybe, get 10,000 photons hitting one pixel, and then the pixel next to it might have some other information, and being able to dissect that information coming in, and I'm thinking of various layers. And so I think you get the point. Okay, next slide. Okay, so where can we find one of these magical real-time adaptive sensors? Besides sending AFOSR a big check, we can, next slide. Okay, that was a joke, sorry. So the sensing modes here that we're wanting to design into a future capability, of course, is spatial. We get the shape feature, spectral, materials characterization, unique fingerprinting of materials based on phenomenology. Polarization, this is an underutilized modality. Many papers recently written about it, about its potential. 3D phase information would be great for LiDAR. You light up objects with LiDAR and you can get 3D unique information about it. Next slide. And I'm not going to go through all this, but there are numerous spectral bands. I come out of I have a space background, so if you look at this, a lot of this, the different wavelengths have to do with looking at missiles and the different phases of flight and whatnot. UV I was always interested in because the Earth is black in the UV by 4 orders of magnitude, so if you're looking at anything that reflects any UV, against the Earth. It sticks out like a sore thumb. Solar panels and the like. And spectral discrimination, of course. If you can't resolve something spatially, say you're in LEO and you're looking out at GEO, you can maybe get information about different wavelengths that could also provide unique fingerprint information. And then the one that's, as I mentioned, was underutilized is this polarization. It's just unbelievable the amount of additional features and detail that you can pull out for enhanced discrimination. And so again, the idea would be to roll all this into a focal plane array. So the opportunity. So I mentioned this, right? You'd like to have this agility for addressability for the different modes, compact, affordability, all that tells us, many of us, that we really need to have a vertically integrated compact device as opposed to having ones that are laid out. Each focal plane array, if it's discrete, requires its own cooler, its optics to get the signature to it. And for example, this pod, the Gorgon's there, 500 pounds it weighs, and a lot of it has to do with the hardware to support the optics going to the 9 different focal plane arrays, as well as the coolers. That's where most of the mass and the cost is. And so these are the sorts of functional capabilities we would need. Bore sighting it, and then have a way to get in there and address and tune and read. And there are many constructs that I'm aware of. Some of them we came up ourselves that are a solution to providing this magical focal plane array. Okay, we know how to do it. Problem is the materials that are needed, many of them are not compatible. So we're looking at that when I mentioned heterostructures. We're looking at ways to find material science solutions for these heterostructures, as well as circumvent that problem, looking at new breakthroughs with nanotechnology and other interesting approaches, right? And so, as I said, the hetero, the dynamic tuning, and I went over this at the beginning. Next slide. Okay, so this then really is, this could have been my very first slide, right? And a lot of people would have been happy, but, so this really is the outline for my portfolio. There's desired functional breakthroughs, and then the scientific opportunity sort of. So these are the things we can't either do these today, or we can't do them well enough to integrate them into coming up solutions for the warfighter for the focal plane arrays. Okay, so a lot of it has to do with dynamic tuning of the band edge and absorption and the wavelengths and photon property, new transduction methods and whatnot. And then these are the enablers. These are the real exciting, hot topics, 6.1, nanotubes, nanocarbon, nanorods, from metamaterial structures, functionalized nanostructures, plasmonic structures, and then integrating all of these together. And so most of when I have the broad area announcement, I include both of these, right? And so most of the efforts, all of them will have some aspect of this targeting, in many cases, trying to solve one of these functional breakthroughs. Okay, next slide. Okay, so what I'm going to do, I'm going to show, I have 10 examples, and then I have a collage at the end if I can get to it, that have another 15 projects on it. So this first one is really, really, really cool, okay? This is a diamond nanowire. It turns out to be, it's an allotrope of carbon. Allotrope is one element, all the different structures of the same element. So you got buckyballs, or C60, carbon nanotube, graphene, graphite, you can't see it, and all these created a lot of excitement. This was in '85 and '91 and 2004, and all these are sp2 bonded. The sp3 is, of course, diamond, and charcoal and coal and soot. Then along comes this accidental discovery of this nanowire. The nanowire itself, I'll show in the next chart, its core is pure synthetic diamond, right? It has the diamond structure, the off-centered FCC lattice, and it has a shell of graphite around it, okay? And when they first produced it, it was by accident. A postdoc was trying to grow very long, very thin carbon nanotubes. So he had methane, hydrogen, nitrogen on an iron catalyst sample. Halfway through the growth, he had to, as the story goes, his wife got mad. He had to go home. It was late, and he turned off the methane and the nitrogen, and he left the hydrogen flowing, and he programmed the cooling process to last for 12 hours. So when he came back in the next day, looked under the microscope, and he had these sorts of structures. They said, wow. So they did all the spectroscopic techniques, and they did the crystal lithography, and they found X-ray diffraction. And to their amazement, they had this new allotrope of carbon. And that was in 2008, and they didn't know how they did it, and it took them for 3 years. They couldn't reproduce it. So eventually, they published it, and I literally said like 3 sentences about it last year. Just next slide. And then, happens to be 11/11/11, after hundreds of trials, they came up with the recipe. And it turned out to be the size of the iron particulates that provided the seeds. It was actually, they went through all the different permutations, and it actually then ended up had to do with the quality and the nature of the seeds. And so what you're seeing here, so these holes, by the way, this is the substrate. These are holes from the substrate in the TEM. And so here you have the sp3 diamond, graphite, the dark, this is pure diamond, this is graphite. The diamond is an insulator, the graphite is a conductor. And they still don't understand, what the transition is between the sp3 and the sp2. And they've been invited to the Royal Society of Chemistry to write an article. And there's a lot of questions still to answer. As I said, they don't know the mechanism, growth mechanism. Potential applications, well, they found that for a single photon source, they know it's better than carbon nanotubes by like a factor of 1,000 due to the physics of threshold voltage and other things. And then they also compared it to Harvard University took synthetic diamond film, and they did a reactive ion etch, and they actually etched down and made their own diamond rods, right? And they were able to find that there was the nitrogen, the NV3 vacancy that produced a single photon, and everyone got excited about it for maybe quantum cryptography and other applications. Turns out that those results, the peak wasn't strong enough and it wasn't stable enough. But they believe now they've come up with another peak at 415 nanometers that is like 50 times brighter, and it's a different defect. It's nitrogen 3 vacancy, N3 they call it. And so they're excited about it. It has potential applications for a number of things. In terms of sensing, I don't know. I mean, these are, if you could make a film of this, we know that when we had carbon nanotubes, we were able to make a mesh of carbon nanotubes that ended up being an excellent transparent conductor. Excellent transparent conductor. So maybe this could be used for current conduits, current conduction. And then the scientific questions, which are interesting, is when the first phase diagram was published for the carbon system, and I apologize, the pressure, this should be in kiloatmospheres, very high pressure. And the conditions that they use to grow these end up being down in the region where it's graphite and metastable diamond. These are between 50 and 100 nanometers, and theory predicts that beyond 7 nanometers, they should not be stable as a solid. So the theory that the original models in the physics and the understanding does not support the growth mechanism. So there's going to be a lot of interesting stuff here, and like I said, there was an explosion of science due to the original allotropes, and we'll see. Maybe he'll get a Nobel Prize. Okay, next slide. Okay, these next two projects have to do with embedding material in 3.5 semiconductors for, we're hoping for a number of applications. Over here, this is percolated metal, okay? And they're able to control the size. The idea is to control the size of the metal using erbium. Erbium is a rare earth. Turns out it's not so rare, but it is a very interesting material. It's in the lanthanum series, down at the bottom of the periodic table, and I think there's about 14 of these rare earth elements. And Chris Palmstrong is really a pioneer. Back in 1995, he published the first theory of these 14 and how they would match up with the 5, the indium arsenide and antimonide. And he could get a wide range of band gaps. It was amazing. It was from not band gaps, lattice constants from 3.5 to 5.5 angstroms, which is great, which means it has potential to lattice match to a lot of different material systems, right? And so the idea here, if it's percolated, is you could embed little plasmonic features within a material system, right? And the size of the actual size of the feature, you could tune to the wavelength coming in, okay? And with plasmonics, you enhance the absorption by orders of magnitude. It goes by the E field squared. So when the light comes in, the electric field sets up a resonance in the plasmonic, and you get this absorption. The idea would be you'd have different material systems that may not necessarily like one another, like in structured superlattices. You can grow multiple layers of material that are not lattice matched as long as they're thin enough and they don't relax. Once you grow 15, 20 layers, then they crack. Well, the idea would be to grow them thin enough, all these different layers that have different band gaps that you're interested in for doing absorption, and embed these structures. And the reason you need a thick layer is something called the absorption coefficient. You need a thick enough material to fully absorb light energy. For silicon, it's like 100 microns because it's an indirect band gap semiconductor. For these 3.5s, it's usually about a micron. So the idea would be you can make thin layers of unrelaxed material and then have these embedded structures that would facilitate absorption immediately. So you wouldn't have, and so this would be a really exciting potential way of getting absorption as you go on. The other is for a continuous layer. Oh, did I mention the erbium is, the F shell's full, partially full D, and so it's, it's got like the 10 orbitals, and it's metallic. It's metallic, semi-metallic, and the idea also would be to come up with continuous layers. And so Chris I've shown his work every year, and he comes up with a different material system, a complete new set of physics every year. This year it's the ternary gallium, indium, antimonide, and he's been growing these rods. These are metallic rods, okay? They're in gallium antimonide, which can be made either metallic, they could be, either semi-insulating, or they can be undoped, N-type, P-type. And the other interesting, so this is 30% erbium. They don't know why, but when he reduces the erbium concentration down around 10%, the orientation of these actually flips up. They flip up. It's just amazing. Woo, go the other way. And so, and this is just showing, this is the view from here. This is the view from here. And so now you're embedding these structures. Oh, and by the way, this is the reflective high energy electron diffraction. And it's just showing that the quality of the crystal that has the nanorods embedded is almost identical to the host material, or the material you grow over. So these are the sorts of things, embedding these structures that are compatible in terms of lattice constant, but have different electrical, optical properties is how we're going to get to new exciting breakthroughs in sensing. Next one. Okay, this is, I should have mentioned. So the last one and this one, they're different material systems, but I started them at the same time, sort of like a mini Muri. Since I never have luck getting Muris, I have to design my own. And so now he's looking at real specific. He's looking at the orientation of the material, and he's growing erbium, and this is luthenium, luthesium, yeah. And he's able to show that the properties of it change depending on the facet, the orientation of the crystal. And he's also come up with a very, next slide, he's come up with large area, continuous, thin films. What this is showing is he's come up with a new way to make it very high quality. He seeds the gallium arsenide with the rare earth, and then he puts a thin layer of gallium arsenide on top, and then he comes back down with the rare earth, and its diffusivity allows it actually diffuses down, and it ends up producing a higher quality film in the end. And so this is just showing the thicknesses of the spacer. What's important here is that, so this is 10 monolayers of erbium arsenide, 5 monolayers. And what he's showing is that this characteristic here, so this is 1 over temperature, the temperature is decreasing, whereas the temperature increases, the resistance increases. This is characteristic of band-like transport in metallic films, okay? So he's saying that these thin films are behaving like nice, uniform, low resistance metallic films, as opposed to the islands. This was other work that was done where there's a hopping mechanism. So he's confident that, and of course, this could be used then for, again, this is the rare earth, right? So it can mix with a lot of combinations of 3,5 material systems. This might be the solution, and it's thin enough. If you're only a couple hundred angstroms thick, it's transparent. So this might be a method to get current out in terms of current conduits. Next slide. Okay, so now the next 2 slides have to do with looking at new approaches for introducing films on top of detector structures to do filtering and modulation of the incoming energy, okay? This one's a little interesting for me. I'm really not a chemist, but Joe Tischler, we're really lucky we have him visiting in the crowd with us, and we got to meet, and I got to understand all the great work he's done in the past in carbon nanotubes and other interesting materials. And so the idea was, an idea I've had for a long time, I've been trying to sell it, no one has been biting for a long time, is to come up with a way, sort of like electrochromics on a window. You put a voltage on it and it gets dark, take it off. So this would be the idea of put a voltage and you'd have a pattern of some material system and it would darken. And you could then change it, put this in a stack, change the orientation, and be able to collect the 4 Stokes parameters. So this would be a way to collect all polarimetric information for any color you're collecting down below. Okay? Now there is, of course, some dimension, the wavelength that is being transmitted as a function of the dimensions, but then you could just be biasing, different alternating fingers. So what we were wondering, this is a high risk, but a neat approach here maybe, is to, well, okay, so this is this lead chalcogenide liquid crystal. He starts with this top C, and I think he told me I shouldn't have had to pee here, but the top C, and then and you have these carbon chains, and then lead oleate, and they put it together and make the soup and heat it up, and then they remove this with centrifuge, and they end up having the lead selenide. And the lead selenide, from what I understand, it has ligands on it. Okay. Now, correct me if I'm wrong, Joe, but they're not quite sure where the charge is coming from, but they're able to put a bias on this, like for example over here, and attract and increase the density of these into an area such that we're hoping we can get absorption. And these do have a band gap. This just happens to be data for 1 to 2 micron, and so they can control it by the growth conditions and the size. And so this would just be, again, high risk, but an interesting approach maybe. And of course, I had to plug work I've done in the last couple of years. You need thin film contacts, and we had breakthroughs in zinc oxide, thin film, and carbon nanotube. Both were good good conductivity and good transmissive materials. Next slide. Okay, and this just shows when they were biasing these, again, they're not quite sure where the charge is coming from, but they're able to get nice alignment. And so further studies would be how dense can you get these, what kind of absorption characteristics, maybe an effective absorption coefficient. Wow. And then they've also come up with some new physics and underpinning of understanding potentially where the dipole in a charge is coming from. Next slide. Okay, this is an enormously, I think, important and promising effort. This is Yalan Lu. I think he's the only American citizen that's ever received China's highest award from science from the president of China. Okay, and he's at the Air Force Academy. Well, this is, I guess, a couple years before he became an American citizen. But he does this phenomenal work. So he does COMSOL modeling and simulation using Maxwell's equations and whatnot. And he's looking at different films, and he's looking at different structured patterns. But more than that, this is a cross-section of a convergent, divergent pattern film. And in between that is where the metal would be, but he's also looking at complex oxides, photorefractive material, and other interesting materials that whose properties, dielectric constant, refractive index can be changed with electric and magnetic fields. And he's able to manipulate and tailor the transmission greatly. So the potential maybe for this would be to have these films on top of, and they do work for a solar cell, I'll show in a second, and have these complex and then bias it and potentially be able to tune the transmission of different wavelengths, polarization states. And this modeling is being, there's experimental results that are being done at Berkeley, UC Berkeley, and UT Austin that are corroborating his experimental work, theoretical work. And he's also done quite a bit of modeling for photovoltaics. Next slide. Okay, I got to get to some of these. And so this is a real breakthrough for feather in the cap of the Department of Defense. This is a project I started just a couple years before the ARO Muri was on it, but this is a type 2 superlattice. They've been able to get a lifetime that approaches that for mercate telluride. The type 2 superlattice is important because the workhorse for the, wow, that's no, it's supposed to be mercate telluride. Mercate telluride is the workhorse for the Department of Defense for mid and long wave infrared detectors. The problem is, back in the 90s, some studies were done. The problem is it has a lot of problems. It doesn't have a natural substrate. The substrate it does have is only available offshore, has uniformity issues, very expensive, and you'd really like to come up with a new solution. And so, next slide. And so the material system that looks very promising. So this is indium arsenide antimonide on indium arsenide, and you're able to control the absorption band edge by the composition and the thickness of the wells. And he's successfully been able to tune these from 4 microns up to 12 microns, and he's getting this very high. These are photoluminescence measurements. He's been able to eliminate what's called the Auger recombination, the very high lifetimes. And so it's not, the lifetime is not as long as it is in mercate telluride yet, but this is a big step. The Air Force, all the services have been pumping loads of money into this over the last 10 years, and it hasn't gone anywhere. So just this last year, this is the first big breakthrough. Next slide. All right, this is another, next slide. Okay, this is an interesting one. This is working towards a 4-color concept, and this is just a proof of concept where light is used to turn on. Let's say it's you have four PN junctions in series, and there's tunnel junctions in between, and you're shining light, and you turn on 3 of them with light, and effectively the device becomes just sensitive to the energy coming into the one that's not biased. And so you're using light bias to then, you can go sequentially through all of the different channels. And so this is just a really exciting way maybe to get higher multiple color photodetectors. Next slide. Whoa. And yeah, so this is just some breakthrough. This is the first plasmonic focal plane array, useful focal plane array, and that's it. And oh, one more slide. And these are all the other ones that that if I had another half hour, another hour, I could.
That's quite a lot of information. We'll take a time.